Welcome to this colloquium. Today it is my pleasure to introduce José Ignacio Latorre, who will present to us a talk on quantum computations and simulations. Usually we would welcome our colloquium speakers, but this time the travel distance is 10 meters from the office downstairs behind here. Originally, José Ignacio is from Barcelona in Spain and has been working in the field of quantum information, entanglement since the very beginning. And in the field he is probably quite well known for starting and organizing the BNUSC conferences. So if you wish to attend those, I recommend you to come with nice questions. With that, I would like to leave the floor to you.
Okay, thank you. Well, it's a pleasure to be here, really. I had this opportunity to spend months away from Barcelona, and I was very happy to be able to come to the CQT and know the region and the people around. So let me tell you a little bit about two things. So although the title I chose has to do with the work I've been doing here, I will also devote half of the talk to basic ideas that we have developed with Levenstein and collaborators on quantum simulation. So the talk will be divided essentially in two parts. In the first part, I will try to tell you about ways of doing quantum simulation of geometry. And the second part will be devoted to the idea of using quantum computation to analyze properties of arithmetics, in particular of prime numbers. Okay? So it will be very general and non-technical, I hope. So let me go to the first. Well, typically I don't use jokes myself in the talks, but you know that Spain is under a very severe crisis. So let me give you a first slide of a joke that appeared in the newspaper in Spain, saying that this is a physicist in Spain producing an accelerator of particles, and he's using a bucket to accelerate the particle. Well, this is not the case. We do have CERN. But let me use the example of CERN. We do have an experiment. We deduce something, and we see something of nature, and we infer laws for what we are seeing. So in the example I'm using, in high energy physics, you do a very complicated experiment. You infer the laws of physics. You think they are describing that experiment. You construct your theory. This is the Lagrangian of the standard model with the Higgs hidden here. And then you go to a new experiment. And I'm picking here a really special case. I'm taking the example of the experiments of core-gluon plasma, where you have more than 300 particles coming out, and you want to know whether this is correct. It's an extreme example of what I would call validation. So we may start with some experiments, we may deduce some theory, but eventually we want to try our theory on other experiments and see that it consistently is correct. Okay, that's the idea of validation of a theory, but how do we do that? So there are many ways that people try to validate a theory. One of them is to do an exact computation. I'm picking here three ideas, integrable models. So there are cases where the theory can be computed analytically to every detail. You have a solvable theory. That's a case of three theories. That's a case of many theories in 1 + 1 dimensions, where you have integrable models. You have the Turing model, the Sine-Gordon model, where you can compute everything there. That's excellent. But this is not the case in general. In general, as soon as you have some interaction, you cannot compute analytically all the observables in the theory. Fortunately, there are other examples where you can guess or you can compute things. For instance, conformity theory. Again, it is not based on a Lagrangian, but yet the symmetries that you are imposing are such that you only have a finite set of solutions to those rules. That's inheriting the old ideas of S matrix and all these things in the 50s and 60s. Or recently, this idea of conjecturing. So you hoped that the result is exact. You can't really prove it. You bring a lot of evidence. This, by the way, is the way many mathematicians work. Okay, they produce conjectures very often they cannot prove. Now you have a second set of techniques. Now you have perturbation theory, you have non-perturbative methods, you have toy models. Take the example of chromodynamics, the theory of quarks. Well, people invented the Bach model, people invented chiral perturbation theory, people invented Nambu, John Arsenio. They invented effective models to describe the theory in a certain regime. Okay? So although this is not exact, it builds confidence that we are dealing with the correct theory. And finally, we have numerics, which is increasingly more and more important. Okay? Because we do have computers. The computers are more and more powerful, so we can try our theories numerically. And the big players are Monte Carlo techniques that are very well suited for a vast majority of problems, but they fail as soon as you have certain properties of the theory, like when you have what is called the sign problem, or in general the phase problem, or tensor networks, something that has inherited a lot of momentum because of the progress in quantum information theory. The way we encode entanglement on a classical computer is something that has improved dramatically over the last 10 years. So all these DMRG, old techniques are now rephrased in terms of matrix product states, multi-scale renormalization group ansatz, the mirror, or PEPs, projective entangled pairs, or in general, whatever kind of tensor network you may try. But do we have other powerful techniques? Indeed. Let me go back to very back in time. No? We have analog simulation. In the spirit of analog simulation is that we all agree that the laws behind the systems are different and peculiar, and they are, they have their subtleties. Yet there is one emerging property of the system that I try to understand in an effective way. I'm taking the example of time, where I use two different ways of measuring time. One is by friction of the sand that falls, or with a pendulum, okay, using a different philosophy. Okay, both of them mimic each other if I only consider the measuring of time. This is the spirit of quantum simulation. I may be interested in a system made of spins with interactions which are very specific and they are found in nature. Yet, I use a completely different system like cold gas, where I tune the properties of the gas so that I mimic the behavior of the spins. So I'm doing a simulation which is quantum, because I simulate a quantum system with a quantum system. So I use two quantum systems to simulate each other. And the very, very inner core of the idea is very simple, that I want to see, I want to have a Hamiltonian on a given system where I do have control on some of the parameters of the interactions. And hopefully I will manage this Hamiltonian to simulate a piece of the physics of the other Hamiltonian. Okay? So that's the basic idea of quantum simulation. And then you may argue why this is good. Well, quantum simulation can be argued to be a natural window towards quantum computation. So maybe, we are living a short period in time on Earth. We are here, passing a few years. So maybe the goal of a quantum computer is beyond our lives. So it's a very natural thing to argue, what can I do in a short period, in a short time, which is useful, yet it is not the quantum computer I wanted to do. So if you think in these terms, you have the classical computer, which is our present reality with all these techniques of Monte Carlo and mirrors to describe or validate theories, we may have a quantum computer, which is by definition a general purpose machine that can handle essentially any computation, because it includes in particular all the classical Turing machines. And there I will run the big things. I will run Shor's algorithm. I will run NAND trees, oracle problems, problems where I do have an exponential gain. Okay? Yet there are very few problems, very few algorithms, and the hardware is far. So quantum simulation can be understood as something which is experimental, achievable nowadays, that if properly thought and designed, it would provide an efficient analysis of some specific problems. And in particular, it can explore systems in non-obvious regimes, or we can even invent things which are not that in nature, but they have interesting properties. So what could be quantum simulate nowadays? Well, here's a short list of things that we could think of. We could do quantum simulations of models that are of interest to us beyond whatever we can do classically with a classical computer or analytically, so that we gain information if we use a quantum simulator. We can quantum simulate very specific things like criticality, quantum phase transitions which are non-obvious, frustration, phases, topological order. So we may explore the boundaries of our analytical knowledge on the systems. We could also be very aggressive and try to claim that we are near the quantum simulation of gauge theories. Okay, so we could even quantum simulate our best understanding of nature nowadays at the microscopic level, because we can tune up things so that they behave as if they had the dynamics of gauge fields. We can even simulate unphysical models. So as you know, there are quantum simulations of the Klein paradox, of the Zitterbewegung, okay, things which are non-existent in QED because the renormalization, so the quantum fluctuations of QED restore these things, well, eliminate the possibility of these things. Yet I simulate the first order QED equations, and therefore I do have all these paradoxes. Okay? And this has been done. And I will talk today about the quantum simulation of geometry. And where? Well, up to you. Okay, I think there are very good progress essentially in every domain of experimental physics. We didn't say, but questions are more than welcome during the talk, okay? Or complaints or whatever. So let me then go to the thing I wanted to tell you about, which is how we could arrange for a quantum simulation of geometry. Okay? So let's go little by little. So you see, we know an example of things going on in this spirit. We know that graphene, okay, provides support for an effective modes that behave as if they were electrons obeying a Dirac equation without mass, as we know. Okay, so we have an example of a quantum simulation which nature has produced for ourselves. So let me not think of graphene. Let me go back to the Dirac equation and see if we can work on it so as to simulate it in a different way. Okay? So can we do that on an optical lattice? Can even we consider a fermion moving on a background, not necessarily a flat space? This work was done with my colleagues Boada, Alessio Celli, and Levenstein, Maciek Levenstein. And the idea is the following. Okay, I said I would not be technical, but there are a few slides with some equations. So this is one of them. I take the Dirac equation, and I pull the time on the left, space on the right. I take a representation for the Clifford algebra in 2 + 1 dimensions, and I rewrite it, and then I take the real Hamiltonian from the Hamiltonian density, and I discretize. So whenever I take a derivative, I claim that my field only lives on a discrete lattice, and the derivatives are the difference between the value of the field at one point in the lattice minus the other point divided by the lattice spacing. So this is my discretization. A is the lattice spacing, and as you see, I simply have the fermion at side Mn jumping to side n plus 1n in one direction, or in the other direction from n to n minus 1, in one direction or in the other direction.
But you see, each side at 0, that is you find, or that is...
Oh no, this is wrong. Sorry. Sorry, my mistake. Sorry. So, but could we look at this equation again? You see, this is the discretization of my model, okay? And now I learned what are the Poincaré indices of the Dirac equation doing for you. They are simply telling you that if I jump from M and N, my two components must twist, okay? They must get changed because there is a sigma x, and the same sigma y. So forget about the Dirac equation and now think at this other level. If I manage to have a physical system where when I jump, I impose this change, I'm simulating the Dirac equation, because that's what finally is all about. Okay, so it's the fact that I have a SU2 Fermi Haber model. Okay, so if this is the point, can we simulate a non-trivial geometry? Let's see that this is indeed possible. So I take the Dirac equation in curve space. My derivative is now a covariant derivative. I'm on a curve manifold. And remember that the curve manifold, what amounts to is to have a covariant derivative. I have to define a parallel transport with a spin connection. So I add to my derivative a spin connection that mixes the local indices. So I have a local guy with local indices A and a curve guy with curve indices mu, and they are connected with a Vierbein. And the spin connection is simply connecting the local bases that you have at two different points. So that's the spirit of the working on a curve manifold. Okay? Well, let's choose a manifold where I still can have conservation of energy, which is sufficient to consider that the metric is independent of time, and reproduce my discretization. The very same thing we did. Well, you see, you have the same things, yet there are some gamma t's of time, and there are spin connections floating around. Now, you keep control of all of them, and you specialize to a particular space-time. So let me go to an example of that. Consider what is called the Rindler space-time. This is a space-time that describes an accelerated observer. Okay, it's like the guy near a black hole. Okay, so this is described by a flat space and a space-dependent coefficient for the time metric. So you see, this is the Vierbeins. You can compute everything, and it has a very nice interpretation. If you add quantum mechanical fluctuations, you relate acceleration to the Unruh temperature, and it is indeed the near horizon description of a black hole. But I go back to the top thing. Can I simulate that on a lab? Well, if you reproduce all the steps I did before and you take that metric, the only change in my Haber model is that the couplings become position dependent. The only thing. So if now you go to the lab and you simply manage to have couplings in your lattice which are described in a given way, for all purposes, you are simulating the motion of a Dirac fermion in a background, in a curved background. And therefore, you should see all the properties. For instance, how the correlators change and how all these kind of things. But you see, here is the very moment where I would like to step up, okay, and watch the whole thing from a higher point of view. What is essential is to understand that geometry is telling me that my neighbor, okay, is nearer or further away. Okay, this, when you go to the action, okay, is the square root of g that you put in the action, is telling you that the space, okay, is like having a different energy content per site, no? because when I move, okay, I need more or less effort. The kinetic term in my Lagrangian carries a square root of g that is telling me here in that zone of space you are penalized if you move, more than if you move in another zone. So geometry is the same as changing the energy cost of jumping from one place to the other. That's geometry. Okay, that's a deep thing of geometry. That's what you put in the action. Okay, it's the action principle. Okay, so again, I forget now everything. You see, if we can modify the jumping amplitudes in our models in the labs, we are simulating geometry. And as
Can I ask you a stupid thing? So first, why do you call that a Fermi Hubbard? There's no interaction term. So
no, okay, I agree. The kinetic.
And second
Yeah.
question, yeah, okay, this terminology.
It's terminology.
Yeah. This is a quadratic fermionic model.
No, this is the one I simulated is the kinetic term only, as I said.
Yeah, right. So this is exactly solvable.
Yeah.
Why do you want to simulate it?
I'm not simulating.
Write down the equation for.
I agree. I'm
ask
not.
your students to do it for you.
I agree. I'm happy.
But still,
Okay, you're happy.
You want a complicated experiment to
No.
to simulate an exact
No, I'm just
solvable
saying.
model?
No, I'm just saying that the key point is if you want to simulate something like geometry, to understand what you should change in your model. Okay, so what I'm saying is that the model geometry is about changing locally the interactions. Okay, that's it. And a given example is a free theory. Okay, and the free theory, the simplest case, which is what I was writing here as an example, would be to modify as in the Rindler space. And this would be the free fermion on a Rindler space. Okay, so that the coupling actually is proportional to the site. That's what is accelerating in one direction. To the site. You see, that would simulate the Rindler, a free particle in a Rindler.
Is a coordinate.
Is a
It's not
coordinate.
mass.
It's not a mass, sorry, Mn. So this is just illustrating that if you want to see a particle accelerating and you want to simulate that, the only thing you have to do in practice is to change the coupling proportional to the site. Okay?
But your J is sufficient to describe the Riemann and spin growth, say, local Lorentz.
Yeah, it turns out that in this particular example, the spin connection cancels. So there is nothing. So you only inherit the density. In other spaces, they don't cancel. In this space, it cancels. So, okay, so this is my point, that if you want to simulate something, okay, one should go to the physical principle that is affecting the thing. Okay, in this particular case, the jumping must be local. It's a cost of energy of jumping is a local quantity. Now, if you want a particular geometry now, one should discuss that. Okay? And from here, the next thing is, okay, so let's do the opposite. Now I want to think whether I could simulate dimensions. Okay, an extra dimension. Is that something I could do? But now I'm starting the other way around. I think, what the hell is dimensions? And then I will try to implement it. So it's like starting before saying, geometry is local weight of interactions, so, and I do it. Okay? So, and dimensions are connectivity. Here you have a cube, okay, but it's not a cube. Okay, let me make a confession. It's written in a plane. You see, it's a plane. So why do we see a cube here? Because we think of connectivity. I think that this guy is connected to this is connected to this, and this is only connected to this, not to this, not to this. It's the connectivity that defines the dimensions. So what will be the probability amplitude from going to here with all the paths as dictated by quantum mechanics? It will be dictated by the connectivity. What are the paths which are allowed for me? Okay? So this is the spirit. Again, it's worked on with Levenstein, okay, last year. And you see, it's again very simple. So you take your Hamiltonian in d plus 1 dimensions. I take again a free Hamiltonian. So I go from q to q plus u. Okay? And my jumps can be in d plus 1 dimensions. And then what I do is that I separate r, which I call d dimensions, plus 1. And just for the eye to see that very clearly, I use different notation. I call r to the remaining d dimensions and sigma to my new one. And I rewrite that thing here. And turns out that when I singularize one dimension, I see that I remain with a jumping in all the dimensions, which are okay, of maintaining sigma identical, or remaining at R and jumping from sigma to sigma plus 1. Let me call sigma species. So I have two options. My species jumps to the next guy, or else I remain in my site and I change a species. Well, let's do that. Okay, that's the spirit. Let's do that. So think, for instance, of polarization lasers that provides two Nautical lattice with people in the ground state and the excited state. They will move in their lattice, each one. They would not talk to each other, but at a Riemann transition that would jump from this guy to this guy, from this guy to this guy, from this guy to this guy, because you use your degrees of freedom to make the Vannier functions to be only relevant in one of the jumps and not on the other ones, that they are exponentially suppressed. So now I would have species moving in dimensions and jumping from a species controlled by us, by a parameter in our Hamiltonian. And when you do that, you can think of what is propagation. Propagation between here and here, okay, you can think of a possible path. I first change a species. I go to the blue. I move in the blue, and then I change a species, and then I go to the other one. So this is one of the very many things you have to sum over. And you know, when you do that, when you do in detail that, when you go back to your description, and you substitute these, and you put the Laplacians, and you have the massive terms off diagonal in the species, and you analyze as a matrix, we know the solution. We know, okay? And how this would be described as a series of the propagator in your dimension plus corrections, and these are the famous Kaluza-Klein modes. Okay, that's a Kaluza-Klein mode. Kaluza-Klein is the way that you have in your dimension to see that there is an extra dimension. Why? Because it modifies the probability amplitude of jumping from one point to the other point. Because I have many other paths, and these are a series of exponential corrections to my Laplacian. Okay. Again, wouldn't that be beautiful, no? To have a simulation of these things. I mean, like saying, hey, come on, it's okay, this is a free theory, let's do it for other theories. But we now would have a method to simulate in a not too complicated way, I think, what would be Kaluza-Klein modes. If you prefer many body observables, which are more easy to deal in the lab, well, you can check, this is a computation of the Hubble model. So here I add interaction, I add all the stuff, and I compute the phase transition, okay, numerically, and I see how the phase transition changes after coupling induced by this Riemann thing goes from 0 to the same value as if it were connecting in my dimension. And what I see is that I start with a critical point as dictated by the 2 dimensions, and from 3 dimensions, and I move towards 4 dimensions. And actually, you can see that the signature in the lab would be approaching the predictions of the Hubble model in more than 3 dimensions, the theoretical predictions that you have there. Okay, so this is my...
Are you talking about metal insulator transition?
Yeah, the simpler superconducting. It's a point only.
And you still have it in 4 dimensions?
Yeah, because we do. Actually, this is a computation of... It shows that you go halfway. The 4D prediction is here, the 3D is here. So it turns out that when the couplings are tuned at having the very same thing, it's a bi-volume. Rather than having a complete 4 dimensions, I only have 2 guys in this new dimension. So you see that the point goes almost to halfway to 4 dimensions. This is again very special. A bi-volume is extremely close to having another dimension because it has opened an exponential number of new paths.
So how many species would you need to
In this particular volume, only 2.
No, for example, you want to simulate some...
As many as points in the lattice, you would need a species.
But you also need the transition matrix.
Yeah, controlling everyone and only it. So actually the other thing is to have an atom with levels, and you control the levels in the atom. Well, that would be the other thing, not an optical lattice, but you have there and you jump and you jump. If you control those jumps at will, and you're not shining all the time, because this is like having dimensions that are there all the time. You can go anywhere. So if you would have these things, then the result you would should observe are those of moving in another dimension.
So one atom with 100 levels.
Well, but that would be an amazing simulation.
100 sites.
Yeah, but look at this. Only 2 already goes almost to the 4, because, and this is conceptually again clear. See, between having 3 dimensions and 4, just having a bi-volume allows for an infinitely many visits, and that produces an enormous jump towards the critical exponent in 4 dimensions. Okay. And finally, this is one of the things we keep doing. Okay, again, could we simulate boundary conditions? Something that has been there so many times, so many years. But it turns out that if you manage 6 guys, you can already make a Moebius band. So you could have something which is very peculiar, simulate physics in a Moebius band. And if you have 9, you have the first Klein bottle. And this would be really, of course, you need a very detailed control of the transitions between 9 people. But yet, you would have the description of a particle moving in a Klein bottle. Okay? Okay, so this was my first part of the talk. And I would say again that I'm very relaxed myself about, I don't know how to say, I think that any progress, any way of implementing progress, experimental progress is good. So I think that this kind of ideas might motivate a lot to how to do things, no? And might be of real interest. Yes?
I get very interesting, but I'm just curious.
Yeah.
If you can do this kind of simulation on the ordinary computer, for example,
Yeah.
Monte Carlo or just specific that comes out.
I'm just trying to give you the spirit of what is the needed ingredient for gravity, 4 dimensions, or 4 boundary conditions. Because then you can take any model and analyze it under those conditions. Okay? So I'm just giving the example that, as Paolo said, I can compute analytically. It's a free theory. Okay? Precisely, I think you need to analyze first the free theory to know what you expect. So things like these. That you know that the propagator is a Kaluza-Klein series of modes. This is something that you understand because you precisely can solve a free theory. Otherwise, it would be impossible. So let me go to my second part, the work I've been doing here. My collaborators are Germán Sierra and Alex Monraz, who is there. And my motivation will be very simple. Look, imagine we build a quantum computer. We have a quantum computer, okay? Down in the first floor, we have a quantum computer. So what do we do with it? We break classical cryptography. Okay, fantastic. Next day, we implement quantum cryptography. So what do we do with the computer next day? I mean, it's idle. We don't have anything to compute with that. I mean, we are arguing all the time that a quantum computer would break cryptography. Agreed. And next day, what? I mean, because we would stop using classical cryptography. So my point is that I think it's worth thinking what we can do with a quantum computer. Okay? So let's assume we have control, and let's see what we can do which might be of interest. In particular, with a quantum computer, which is not 100,000 qubits big. Because again, if I want to kill classical cryptography, where we are using codes of thousands of bits. So we need a quantum computer which is really powerful. We cannot do it with 100 qubits. We need many more. Okay. So again, are there things that the quantum computer could do better than classical computers, and which are not at this huge number of qubits? So the original idea with Germán was to think whether we could use quantum computers to do computation in mathematics, in arithmetics. And the idea, I flash it right away. The idea is to think what could happen if we manage to construct a state which is the superposition of all prime numbers up to those that are able to be written in my register. So I have an ion trap, and I have 8 qubits. So I can place there up to 2 to the 8 numbers. So let me make the superposition of those states which are a prime number written in that computational basis. Okay? Let's think what could happen if we do that. And here I've written the normalization of the state. You see, it's a state with all the coefficients equal to 1. The normalization simply counts the number of states because all the states are orthogonal. Okay? So this is the prime counting function, which is one of the fundamental functions of arithmetics. It's one of the functions with the largest and deepest history in mathematics. So actually it deserves some time for it. Okay? So again, think what could we do if we could build superpositions of these people. Okay? As an example, the pi 4 will be 2357 divided by the square root of 4. So what is the normalization of prime numbers, of this prime state? As I said, it's a prime number counting. It's a function that was studied by every mathematician, I would say, till the 20th century. I guess there is not a single big name which is not in the list of results of these people. And we know a few things. We know from the time of Gauss and Legendre that pi of x would obey a law, a dominant law, which is that there are as many prime numbers as up to x as x divided by log of x. Okay? This counting comes from the Eratosthenes argument. I mean, you count how many people you sieve with the algorithm by Eratosthenes, and then you deduce that this should be the leading term. But then there were other people, among them Gauss himself and Riemann. Riemann produced a memoir that was 8 pages long, proving or arguing the result, which is nowadays called the prime number theorem. So I cannot resist to say that it would not be published in PRL. And the argument is based on a completely different philosophy. It's the fact that the density of primes go as 1 over log. And if I take this for granted, then the integral, the log integral of 1 over log, which is called the log integral, it would behave as x log x plus a complete series of x divided by powers of logs. And he argued that this was the dominant behavior. Okay? The theorem was finally proved by the end of the 19th century by Hadamard and de Lavallee-Poussin, and it is now called the prime number theorem, which is that the dominant behavior of primes is this. Okay? Now, people have used classical computers to analyze these things heavily. In particular, the latest number is by Platt. I think he is now at Bristol, where the number has been computed up to 10 to the 24. So I take advantage of this to remind you that 10 to the 24 is 80 qubits, bits, 80. Okay? So we are dealing with things which are below 100 bits. Okay? So this is the actual number of prime numbers that we have there. And indeed that this approximation is worse than this approximation, you can check that the difference of the actual number of prime numbers versus the estimation by Gauss and Legendre is 10 to the 20, and there are a total of 1.8 times 10 to the 22, versus this, where the difference is only 10 to the 9. So as you see, it's an impressively better estimate the log integral. And here comes a twist, okay, which is one of these very profound things in mathematics. Turns out that Riemann managed to show that if the Riemann conjecture is correct, then there is a bound on the fluctuations. So let me remind you, the Riemann conjecture says that if you take the sum of 1 over n to the s power, and you look at this function as a complex variable on s, this function has zeros. In particular, if you focus between real part of s between 0 and 1, the conjecture says that all the zeros are lined up on the vertical line at s equal 1/2, real part. Okay? This is a conjecture. Nobody has proven it. And it's considered one of the main problems in mathematics. One of the most relevant problems in mathematics. Well, Riemann managed to prove that if this is true, then the difference between the log integral and the number of prime numbers is bounded by square root of x log of x. If it is not true, this bound is not correct. Okay? So how the number of primes deviate from the log integral is related to where the zeros of the Riemann function are. Okay? So that's very profound. Let me say another thing, that these numbers at present, up to 10 to the 24, they have never fluctuate. So one is larger than the other, and that's it, all the time. But the big mathematicians of the early 20th century, so that is, Hardy, Littlewood, they proved that there must be infinitely many fluctuations of this number, changes of sign. And indeed, it's a branch of arithmetics to know when this will happen for the first time. And the present bound is that a first change of sign will happen before the exponential of 728. Okay? These are called skew numbers, and they are again very impressive. Okay? So let me go back to quantum mechanics. Could we use quantum mechanics to say anything about these long-standing problems in mathematics? Could we use it in any possible way? Could we use them as we are using nowadays classical computers? So could we use them as a substitute of classical computation? Or does the prime state, as a state, is it very entangled? Can we construct it, at least theoretically? Well, the first question I can answer, that's easy, and that's why I do it, is that how entangled is that state? Okay, that I can answer. And that's very easy. I take the state, I write in the computational basis, and my p's are 1 or 0, depending whether the number is prime or not. Okay. Now, I, for instance, use as a measure of entanglement for the qubit 1. I'm labeling 0, 1 up to n minus 1. For the first non-trivial qubit, what is the reduced density matrix? So I sum over all other coefficients, I integrate out everybody. Alice and Bob. Bob is the rest of digits, Alice is one of the digits. And then I compute the reduced density matrix. And when I do it, it's very peculiar. You can check here in particular. I'm computing the reduced density matrix of this guy. There are no prime numbers finished by 0, 0. There is one finished by 2. And the rest either are finishing in 1, 1 or 0, 1. If I count how many of them are in a given category, okay, so I can check that those are the number of prime numbers that when I divide by 4, the rest, the modulo of 4 is 1. Those are, again, series of prime numbers which are very well studied in mathematics. So it turns out that the actual measurement of the quantum system would deliver the functions that mathematicians are studying. Okay? So they simply counting of sub-series of prime numbers are encoded in the density matrix of the prime state. Moreover, I can prove things like that the entropy for one qubit is always 1 in the leading term using properties, again from mathematics, the Tottian function property. Or I can see that the experimental measurement of sigma x would produce, for instance, the twin primes, modulo 1 if I divide by 4. or that the sigma z, if I measure, would produce what is called the Chebyshev bias, the difference between 4.3 and 4.1. And all these are, again, well-studied properties in mathematics. So what is the spirit of what I'm saying? That the entanglement properties of the prime state codify arithmetic functions. Okay? Now, what about multipartite entanglement? Well, my argument is very easy. If it were not very entangled, the state, I would use a tensor network to simulate it, and I would compute all these things on a classical computer in a very efficient way. So it is expected that the prime state will be extremely entangled. And indeed, this is our computation, and you see it grows linearly with the size of the system, with a very precise number in front. So can I made a little joke for mathematicians here. There is entanglement in the primes, because you may know that if you take the primes and you perform the Fourier transform, the support of the Fourier transform has a discrete support if the Riemann conjecture is true. And these mathematicians have talked about there is music in the prime numbers. Okay, so I'm just because of the discrete support, like notes. Okay. Like frequencies that are discrete. So I'm just making a little joke that there is entanglement in primes. And again, another non-trivial property, if we check all the possible partitions, not necessarily first and halves versus and halves, it turns out that the partitions, all of them are very entangled, but the most entangled partition is the original one, the ones that I separate the first and half digits versus the and halves second. We don't know why. Okay, here is the rank of entanglement. Okay, the ranking of entanglement. Let me remind you that if you are working in 1+1 dimension with finally correlated systems, so systems in one dimension which are not at the quantum phase transition, you expect typically entanglement which is a constant. It saturates due to the existence of a finite correlation length. If you go to quantum phase transition, they scale with a log of the size of the system. This is why we can't simulate these models using many techniques, because the amount of entanglement in the system is limited. It's severely limited. If you go to more dimensions, you find the famous area law, the area law of a black hole. Okay, the entanglement entropy that, according to the conjecture of ADS, says that it's related to the black hole entropy. Well, it turns out that this area law emerges naturally when you have local interactions and translational symmetry. Now, this is the power law of n. Okay? Maximally entangled states are n. And the prime number, prime state scaled almost as the maximum possible that it can do. Okay? So that means that if I have the register and I read half of it, I'm maximally surprised when I read the second part of it. I have no way of predicting which will be the prime numbers. Okay? It's a measure of surprise, and prime numbers do carry a lot of surprise. So,
Excuse me, as this prefactor, the 0.8.
I have not been able to compute it yet. I think it will emerge from the
So the
prime
question was, does it have some
meaning. Yeah, I think it is related.
Should have, right?
It should have,
It would be cool.
and I think it's related to the prime number theorem behavior. So to the leading term. So I think that the fluctuations are behind, and the leading term will dictate 0.88. And we have some evidence which is very peculiar, which is there is a thing called the Ulam spiral, which is another way of constructing prime numbers that seems to have no surprise. And when you perform again a state based on that other basis, and you cut and you compute the entropy, it turns out to be 8.8 again. So I think that 8.8 is related to the way primes disappear. No, they disappear with a log of x. No, so I think there is a deep meaning to this number, but I have not been able to compute it. Okay. So can we construct the prime state? Here comes the fun part. Well, little by little. Imagine I start with 0. I do Hadamard's, and I have a primality box. Simply says whether the number is prime or not. Okay. So if I apply because I apply in parallel. I have the coherent superposition of all numbers. So those that are prime will form a state, and those that are composite will form another state. And my ancilla will discriminate whether I'm on the set of states that are obeying that or not. And then I perform a measurement on my ancilla, and with a given probability, I will project on 0. And therefore, I have created my state. What is the probability for that? Well, if the prime numbers are correctly, we believe that P of x goes as x of a log of x, the probability is 1 over n. And n is the number of qubits. So it's efficient. It's efficient. So I could construct 100 of these guys if I have the box in an efficient way. Okay? So this is like, hey, at least it's efficient. Now, the box. Well, before the box, but we can play with many things now. Can I build twin primes? Yes. You take the prime state, you add up 2, and now you run again primality. Okay? So I separate then those that p plus 2 is prime and those that p plus 2 is not prime. Yeah, I measure, if I collapse on 0, I have all the twin primes. So I have made the state of twin primes. And here we are getting to something which is not that trivial, because we don't have theorems about the counting of twin primes as good as we have for others. Actually, the subseries are not well understood, whereas the quantum state would be simply constructing them. Okay? I have another construction for, I'm not writing it for other properties of prime numbers, well-known properties of prime numbers. Could we even be a little bit more clever? Well, could we use the Grover algorithm? Look, the advantage is that now, in the division of all the states between what is solution and what is not solution of the oracle, there are m solutions versus m minus n. And m are a lot, because those are the prime numbers. Actually, when you do it, the number of calls to Grover is the square root of n, of the number of qubits. It's extremely efficient. So let me say that n is 100. Okay? So if this is 100, typically, as you see, in 7 steps, you would generate it. Even more efficient than the previous method. Okay? But for all these things, you need the oracle. And here comes the heavy part. I promise not to be technical, and I will not be very technical, but this is where you have to go down and, you know, to get dirty with things. Indeed, building a quantum oracle is possible because there is a magnificent thing, which is that there are classical primality algorithms which are efficient. Okay? In particular, I am showing you one of them. It is called the Miller-Rabin test, developed along the second half of the 20th century. It's, you know, every little improvement of that test took 20 years. The famous AKS test developed in India in 2002, it's simply more complicated to build into quantum things. It's not that it is impossible, it's simply more complicated. So that's why I'm using the Rabin-Miller test. Look, it's a way you simply can program that on your computer. Okay? You take x, you want to know whether it's prime or not. You subtract 1 because they are odd in general, no, except for 2. And then you take out as many factors of 2 as possible. So any number, it's d, which is an odd number, times 2 to the s. Okay? You take 11, you take 1 out, 10. I divide by 2, I have 5. So s would be 1. Okay? Then you choose what they are called witnesses. I call a between 1 and x. It's a witness for primality. And the test you run is the following. You take a to the a different from 1, mod x, or a to the 2, it's not well written here. R, well, it's written, but I don't know if you can read R, where R goes from 0 to s minus 1. And then if you passed all the tests, you're guaranteed that the number is composite. Okay? If not, you don't know. It might be composite, it might be prime. These are called, the witness is then called a liar. Strong liar is a guy that stubbornly passes all the tests and tries to deceive you. The good thing is that if you have a strong liar, you can run with a different witness, and actually you can prove that with a log X number of witnesses, then you cover the thing. So you finally have a deterministic test. Okay? So it's efficient because all the computations which are involved are polynomial in n. Actually, n to the 6, I think. Okay, so you do that in quantum mechanics through gates, and I will not enter in a lot of detail. I simply, you test the things, you have carriers, then you analyze all the carriers, and you finally say yes or no, and then you undo all the gates, as you do in a standard way in quantum computation. And then the detail of the test, you have to be careful, because whether you use S1, S2, S3 is due to the decomposition, but that decomposition can be done with controls. So you simply keep the control finding what is S, and then I act with my witnesses. And there is even a little detail extra about the size of X, whether certain tests have to be done or not. Again, you can control. Okay. So the point is that you can control all these things. Okay. So then everything is possible. The quantum algorithm, it's polynomial effort. Okay. The construction of the state is polynomial effort. And the final magic comes when you combine the quantum oracle with the quantum Fourier transform. And this was done many, many years ago, in '98, by Brassard, Hoyer, and Tapp. That the idea is that you do these Grover things, and every time you hit one digit in a register, which is as big as you wish, and the Fourier transform of that guy will eventually let you know how many solutions has the Grover algorithm. This was an algorithm by, as I said, in the '98, and it is called quantum counting. Well, you do it, and it turns out that the statement that you can find is that if you make a constant times a square root of n calls, you will assess m, the difference between m and your estimation of m tilde, with a precision which is less than, well, so with an error which is less than m to the 1/2. Now, if you substitute m tilde by the counting prime numbers that we do, m prime by the log integral, m by our counting, and m is again this. So it turns out that this algorithm would fix the number of prime numbers, the fluctuation, with a precision which is bounded by x to the 1/2 of a log of x. And when now you compare to the Riemann conjecture, it turns out that your precision is better than the fluctuations dictated by the Riemann conjecture. So that means that formally, the quantum algorithm, it's better than a classical computer. And on top, it works in a square root of time. Okay, so let's be clear. You gain time, but the measurement is not 100% because it's quantum mechanics. You have probabilities. So it turns out that you can relax the probability. The probability is bounded, the error is bounded, maintaining the efficiency of the algorithm, okay, which is something which is not obvious a priori. So this has to be compared to the best possible algorithm nowadays by Lagarias, Miller, and Otzilo. And this algorithm has been used by Platt, as I said, and it runs with time x1/2, but space x14. So they need, the natural thing is no space and time t, and the trade-off has been improved up to that the product is t by s is 3/4. So in quantum mechanics, you beat that. So this was my example that one could tune a quantum computer to do these things, and that to surpass classical power of machines, you only need to have under control 100. As I said, 10 to the 24 is 2 to the 80. So at a few hundred qubits, a quantum computer would already beat all the classical computers. Okay. So let me be one more transparency plus the conclusion. And the second is that this, in a way, is not prime numbers. Any mathematical series of numbers, the zeros of the theta function, the Dirichlet characters, the twin primes. I mean, there are many series of numbers whose properties we are interested in. And this can be done, to use a big name, thinking that there is an application of sets into states call it functor. And the functor, the natural functor, would be constructed by just having oracles that decide whether this character is a 1, a 0, or a phase, or whatever. So there you can map, okay, these questions in mathematics to questions that are experimentally observed in quantum mechanics. Okay? And finally, my conclusion. So from the first part, it is just about basic concepts. And my point was that geometry is site-dependent couplings, dimensions are connectivity, and boundary conditions are non-local couplings. If you can arrange for these things, you have simulations of those things. Now, the model you want to address with that, it's up to you. Okay? And in quantum simulation, that superpositions of series of numbers are possible in quantum mechanics, and if you have an oracle, automatically, then the properties of the functions are measurements, okay, for us, and that very likely this is our first approach. And I have heart in my, somewhere in my heart says that there are more efficient ways of doing these things that we haven't been able to see. So thank you very much for your attention.
There have been a few questions during the talk, but are there any more questions?
Too far-fetched.
You mentioned the phase problem or sign problem of the lattice like that. Do you have any example of the problem which cannot be handled by the conventional Monte Carlo, but your quantum simulator solves?
Yeah, all the simulations of people who are doing now gauge simulations, they are not doable with Monte Carlo because there are phases in the plaquettes, and they are doable with tensor networks.
Any more questions? If not, we thank the speaker again.
Okay.